All right, so welcome back, everyone. So today it's my pleasure to welcome Florian Schaefer. We'll be talking about statistical inference and PDEs from operator learning to show capture. Yeah, thank you, Florian.
All right. Thank you very much. Thank you for coming. Thank you for inviting me. So today my the talk I'm giving today is going to involve sort of three sort of parts that are all organized around this idea of advancing numerical computation, oftentimes fairly classical problems in numerical computation, using insights from in this case actually statistics, not so much games for this particular talk today. And so I start by talking about the use of conditional independence for operator learning of elliptic PDEs. And then there will be some sort of application of that to problems in the coarse graining of operators arising in Navier-Stokes, so elliptic fluid dynamics. And then finally, I'll talk about a somewhat different in spirit line of work that uses information geometry to regularize hyperbolic conservation laws. So the first work is a joint work with Humano Hadi that is now appearing or about to appear in CISC. And so the rigorous result is as follows. We assume that we're given a domain omega in Rd that has a Lipschitz boundary. And we're given some linear elliptic PDE. And so for simplicity, we assume that it's a divergence form. So it's the resulting map from H0s to H minus s is symmetric and positive and local. So for instance, you could think of the Bilaplaschen that we have here, but you can equally consider any type of rough coefficients, arbitrarily high order, and so on. So we care about elliptic PDEs. And then we define as G the sort of Green's function of that elliptic PDE. So which is basically the solution operator for Dirichlet boundary conditions. And so this is how such a Green's function looks like. If I plug in one particular value, and then the solution of the PDE for a given right-hand side is obtained by computing the convolution of the right-hand side with this Green's function. And now we will be concerned with two types of discretizations. The first is if the order of our elliptic operator is large enough so that the solutions are defined pointwise, we can discretize this Green's function, so the solution operator, simply by throwing a bunch of points in our domain, such that the ratio between the smallest distance between 2 points or the biggest gap without a point is bounded, so they're roughly uniformly spread in the domain. Alternatively, we can, in the setting where our solution is not pointwise defined, we are going to use some sort of hard-type basis functions. So it could look like this, or for instance, if you have access to a solution operator through a finite element discretization, you would basically be using linear combinations of whatever are your finite element basis functions in order to reproduce some Haar-like basis function. And it's not so it's not so important how exactly these basis functions or these Haar basis functions look like, just that they overall have this idea that you have like a coarser scale thing that is constant, and a finer scale thing that is sort of like differences that are orthogonal to this coarser one, and so on and so forth. So there's some kind of like recursive subdivision multi-resolution type decomposition. And so either way, we now have assume we have access to this discretized Green's function, which we will call this matrix theta. And now what the problem that this work is concerned with is, imagine you get to choose a bunch of right-hand sides f, and you get to observe the product theta times f. So basically the solution of our discretized PDE with that right-hand side f. And so these are the UI. And now what we want to do is we want to be able, just from observing a few of these UI, we want to be able to reconstruct a good approximation of the discrete solution operator theta. And of course, the name of the game in these kind of things is that we want to get as accurate as possible an approximation of the Green's function from as few solutions that we observe as possible. And so in particular, we want to choose these right-hand sides f in such a way that they give us as much information as possible about the Green's function and therefore the solution operator. And so we could wonder, why do we care about this problem? And the first, and I think maybe the most at least in the current world of applied mathematics, probably the most salient motivation is that this really gives us a sample complexity of learning elliptic solution operators. So given an elliptic solution operator, how many solutions do I need to observe in order to get how good an approximation of that solution operator? So it's, yeah, the sample complexity of learning PDE solution operators. And of course, that, the reason this is sort of a popular topic right now is that there has been a lot of work using neural networks and kernel methods and other machine learning type methods in order to directly learn the solution operators of PDEs. And so there's the question of how, like, can we characterize, at least in this simpler linear elliptic case, how well we can do in this. And then there are some ongoing lines of work of using this for inverse problems. So we can first maybe learn the solution operator or Dirichlet-Neumann operator, and then afterwards query it sort of offline in order to solve an inverse problem. And finally, there might be some case where maybe we have a legacy solver that is slow and non-parallel, and that we want to sort of compress in a new format using just interacting with it as a black box. And so before providing, talking about the results, I want to briefly talk about related work. So arguably, the first sort of rigorous results were based on eigendecompositions. So the problem with, so the idea, so somehow learn like a global low rank approximation of this operator. The problem with this is that it generally leads to a polynomial, or to a cost that's inverse polynomial in the target accuracy, because the singular values of elliptic solution operators decay only algebraically. So they decay like an inverse polynomial, and correspondingly the number of degrees of freedom I need in order to, or the number of solutions I need to sort of press down the error below an epsilon is inverse polynomial in epsilon. Now, actually older than this, there was like purely empirical work targeting the H matrix structure of these operators. So instead of just looking at them as operators that possibly have a have a low rank decay, the work by Lin et al. And Martinson was looking at them as operators that have submatrices that have a fast spectral decay. And so it's well known that these solutions operators of elliptic PDEs can be approximated much more efficiently using hierarchical low rank structure than conventional low rank structure. However, because of the difficulty of controlling the error propagation as one sort of like tries to reconstruct these hierarchical low rank matrices from matrix vector product, there are no rigorous results on the learning of PDEs. And what you see here on the right, this rate for M, that is the rate for M one would hope for if everything were to go as well as one could imagine in this error propagation, but it was not done, so there was no actual rigorous results. Then there was, more recently, there was a work by Boulay and Townsend that provided a rigorous proof. However, it was still having a polynomial or inverse polynomial cost, so inverse polynomial in the target accuracy, and it also relies on this property gamma epsilon that is again depending on epsilon, and that does not have, at least the authors do not have any bounds for. So in some sense, it does not constitute any sort of asymptotic sort of sample complexity, because in principle, this gamma could become arbitrarily small. And then after our work, Boulay, Halikia, and Townsend extended this to make use of the hierarchical matrix structure to remove this inverse polynomial complexity, but still featuring this gamma epsilon that is a priori unbounded. And so in this work, what we do is we show that one can construct an epsilon approximate so representation of the solution operator from only log to the d+1 matrix vector products and a near linear amount of computation. And so by choosing n such that the discrete that's large enough to approximate the underlying continuous operator, this means that we basically get the rate of log to the d+1 of 1 over epsilon for reconstructing the solution operator for matrix vector products. And so I want to point out that this rate is better even than the sort of the best possible rate than what one would have one could have gotten with the H matrix approach if one were to sort of rigorously track the error there. which is due to the fact that that we are going to use a slightly different type of compressed structure that is more efficient than H matrices. And so what this does is that it settles the question, or it establishes for the first time a rigorous logarithmic sample complexity of learning elliptic solution operators from data. Okay. So how are we going about this? And so the first element that we're going to use is we need some kind of simplicity of a way in which this matrix theta is more special than any arbitrary matrix. And for this work, what we're going to, and the kind of simplicity that we're going to target is the fact that, as we had shown in previous works, that these matrices theta actually have almost sparse Cholesky factors. And so, as a reminder, the Cholesky factorization amounts to the following. It amounts to reordering the rows and columns of the matrix, or the sparse Cholesky factorization amounts to reordering the rows and columns of the matrix, choosing a sparsely set, and then, so having a sparse Cholesky factor means that the Cholesky factorization, so the product L times L transpose of theta is essentially only has entries according to this smaller sparsely set S. And so in the example where we are discretizing our solution operator through a bunch of scattered points, it looks as follows. So we first need to choose the ordering of the rows and columns. And this ordering is going to be obtained by successively selecting the point that is furthest away from the point that we selected before. So we keep trying to spread out the points as far as possible from each other. So as we are ordering the rows and columns, we keep selecting the row and column that is furthest away from the rows and columns that we have already included. And then we choose the sort of geometric sparsity pattern where for the first points in our orderings, we keep the entire column of non-zeros. And then as we move to later points, we keep decreasing the range within which we keep track of the entries. And so as a result, this sparsity pattern that we're going to use means we have a few sort of dense columns at the beginning. And then as we move to the right and have more and more columns, we're keeping track of a sort of more and more sparse set of non-zero entries. And in analogy for the wavelet, in the wavelet case, what this means that if we write our Cholesky factorization in a wavelet basis with the wavelets ordered from coarse to fine, it means that the columns of this Cholesky factor are exponentially decaying on the scale of the wavelet that they're associated to. And so here, for instance, the first columns of this Cholesky factor, they correspond to coarser scale wavelets like this one here. And as a result, the resulting column actually decays exponentially on a scale that is commensurate with the sort of scale of the support of the wavelet coefficient. And then as we consider more and more fine scale wavelet coefficients, so these are the wavelets on the left, the corresponding columns of our Cholesky factor become more and more localized. And so we can, again, so this error decays on exponential scale, so we can get a good accuracy by sort of choosing an oversampling radius rho and just cutting off the contributions outside of rho times the scale of the wavelet. And so we can wonder now, so before I talk about how to use this idea for, before I talk about how to use this idea for operator learning, I want to briefly give you a hint of why this property could be true. So why these dense matrices theta, these dense solution operators, can actually have sparse Cholesky factors. And the reason for this is that if you compute a Cholesky factorization, it's really an iterative application of this of the matrix identity I have here. And so, in other words, computing the Cholesky factorization reveals the conditional expectation and conditional covariance of a Gaussian process distributed according to this with this theta as its covariance matrix. And so, in other words, the sparsity of the Cholesky factors of theta are directly related to the conditional independence of a Gaussian process that is distributed with theta as covariance matrix. And so in previous work, we had studied the conditional independence properties of these Gaussian processes. And we found out that one can prove that after conditioning on sort of coarse scale degrees of freedom or conditioning on the evaluations of the random process at a few points, the conditional correlation length decreases dramatically. And so that's what you see in this GIF, that as we condition on more and more points, the conditional correlation length that you see shaded in orange becomes smaller and smaller. Let's wait for it to start one more time. Right, so as we condition on more points, you see that the conditioning on these nearby points decrease the correlation length. And we were then, by using tools from numerical homogenization and operator wafers, we were able to prove this rigorously. Okay, so this was this was a bit brief, but it's just to say these in the right basis, these matrices theta that we're trying to recover, the discretized solution operators, have sparse Cholesky factorization. So you can write them as L times L transpose, where L is a sparse lower triangular matrix. And now we want to use this sparsity in order to efficiently reconstruct the matrix from just a few matrix vector products. And so the first idea that is going to be important here is this idea of graph coloring. So imagine we have a sparse matrix that you see on the left, and we know the sparsity pattern of the columns. And again, because we have this geometric insight into what the sparsity pattern of these Cholesky factors look like, that's a reasonable assumption. And then what we can do in order to more efficiently reconstruct this matrix is that we can identify, let's say, 3 columns, the one that are colored here, 3 columns that have disjoint supports. And so then we can multiply them with the right-hand side that is specifically tailored to only activate these 3 columns. And that then is going to produce one vector that has the coefficients of all the 3 columns written together. And so what this means is that we can reconstruct 3 columns of the matrix at the price of just one matrix vector product. And we can actually do the same thing when dealing with a, if instead we are dealing with a sparse Cholesky factor, where the leading columns of the Cholesky factor have disjoint support. Again, when we multiply this with a suitable right-hand side, then we get sort of one vector return that contains the non-zeros of all these 3 leading columns. And this is really important because basically, I mean, if our singular value decomposition, or the singular values decay at a polynomial order, but we want an exponentially accurate algorithm, the only way in which this is possible is if we have some mechanism that allows us to get multiple matrix vector products for the price of 1. And this is exactly this mechanism. This is what allows us. Normally, one matrix vector product would give us 1 column, but by exploiting sparsity and our knowledge of the sparsity beforehand, we're able to exploit to sort of get multiple columns, multiple matrix vector products worth for just one matrix vector product with very particularly chosen right-hand sides. And so physically, this is how it's going to look like. So imagine, so here we have some sort of, we have a bunch of wavelet coefficients on one of the finer scales. And so this is the resulting part of the, this is the corresponding part of our Cholesky factor. So you see the sparsity pattern. And now again, we are choosing our right-hand side so that it matches, it's sort of like, it activates only such sparse columns that are disjoint to each other. And so, for instance, in this wavelet case, what we could do is we could use this right-hand side as a right-hand side here. We could use the function on the left that has all these sort of well-separated pulses. And then after multiplying with our after computing our Cholesky factorization, we would get the corresponding, we would get the sort of the output on the right. And now you see that because all these pulses are sort of non-overlapping, they're like not interfering with each other, we can then cut them up and treat each of them as a separate matrix vector product. And so in this case, we would get 16 matrix vector products just for the price of one matrix vector product. And now there's one more problem that, if you remember from the beginning, we had this issue that we have some sort of wavelet coefficients, the coarser wavelet coefficients, that are bigger than the finer ones. And so that means that we can squeeze fewer of them into the same, matrix vector product. And so it would be a big problem if we had to deal with this sort of the size of these bigger wavelet coefficients throughout, because it would greatly limit the amount of sort of tricks we can play in sort of squeezing as many matrix vector products into one matrix vector product. However, we can use this peeling strategy that was used in a somewhat similar form by Lin et al., where after we identify, let's say, the column corresponding to this causes wavelength coefficient in red, in our subsequent matrix vector product, we post-process them by subtracting the corresponding part of the Cholesky factor. And so that removes this leading dense column and reveals the sparsity on the finer scales of the Cholesky factorization. And then so the resulting algorithm that we call Cholesky recovery looks like this. So we start with like an empty matrix, and each time we basically we treat a new column out of this matrix O that we get by multiplying theta with the suitable measurements. We subtract the part of L that we have computed beforehand, and then we scatter the result to get our multiple sparse columns from it, right? So this is the scatter operation that takes 4 sort of like independent parts that are written in one vector and writes them as like 4 separate vectors. And then we add these new columns to our matrix L and proceed to the next final level. And then the main challenge is that, I mean, that one has to rigorously prove control the error propagation there. So there are some tricks here, but I will sort of glance over them. I'm happy to answer questions after the talk on that part. And there's also some sort of further results, like we have it seems to work on fractional operators, and it seems to work on an LU variant. But in the interest of time, I'm also going to defer a detailed discussion of this, and I'm just going to show you one maybe example on a 3D problem here. So here we're dealing with a 3D problem in a non-uniform mesh, and we are increasing the this oversampling parameter rho that determines like how many basis functions we are fitting into one matrix vector product, because there's always like a small overlap between these basis functions. The fewer we fit into one matrix vector product, the more accurate we are, but at the cost of having to do more matrix vector products. And so we see here, as expected, the sort of exponential decrease of the error as we increase rho. But regarding applications, I want to now talk about a more sort of real-world application where this was already deployed, which is joint work with Spencer Bryngelson, Jesse Liu, and Ali Mani, which arise in fluid mechanics. And so there is this the application we have in mind there is the so-called macroscopic forcing method, which is a way basically, if you have some sort of Navier-Stokes-type solver, you want to basically run this Navier-Stokes-type solver for a long time horizon, and then you want to average it, for instance, over time. You want to average the solutions over time, or you want to average the solution over one spatial component, for instance. And then what you're interested in is you want to find an effective solution or an effective sort of coarse-grained operator that governs the solution of the linearized Navier-Stokes with respect to these average degrees of freedom. And so it turns out that this averaged sort of or coarse-grained solution partial differential operator can be characterized in terms of a non-local eddy diffusion coefficient. And so this eddy diffusion kernel looks like what you see on the bottom left. And so in particular, it looks kind of like a solution operator from elliptic PDE. And so that was what motivated us to say, okay, we have this mechanism for reconstructing elliptic solution operators for matrix vector products. And Mani and Park have this mechanism for computing matrix vector products with this eddy diffusivity operator, computing such matrix vector product at the cost of a sort of average Navier-Stokes solution. And so the interesting question is now, can we use our mechanism for squeezing more information out of each individual matrix vector product? Can we use this mechanism in order to accelerate the computation of these eddy diffusion operators? And that's quite important because, again, like basically, if you do naively, every single column of this matrix, and this matrix is as big as the number of coarse-grained degrees of freedom, every single column has to be obtained by running one like long-time Navier-Stokes solution and averaging it. So there's a big interest in sort of trying to reduce the number of times you have to do this. And so this is where we got, I'd say, pretty promising results, even though it's not, I mean, we don't have a proof that these L diffusivity operators fit exactly into the framework or the theoretical framework that I outlined earlier. It seems that this sort of reconstruction in the LU variant works pretty well. So we see that so here in dark green, you see the sort of, you see the randomized low rank approximation for comparison. And in gray, you see the approximation based on the SVD, which is, of course, inaccessible because you don't have, I mean, you can't just compute the exact SVD from only a few matrix vector products. But we see that even compared to this exact singular value decomposition, so the optimal low rank approximation, we can do significantly better by using this peeling-based method, so our LU recovery approach. And so we also tried this on a turbulent channel flow where the difference of what we can achieve with this peeling method is even more significant compared to the randomized SVD. So here we see, like, on some problems we see improvements of 2 orders of magnitude in accuracy for the same number of matrix vector products. And now if we're using this coarse-grained operator to actually simulate the coarse-grained Navier-Stokes equation, we also see significant sort of phenomenological differences in the solutions obtained by, let's say, the randomized low rank approximation, which has features these unphysical oscillations, compared to the sort of solution with the coarse-grained problem that we obtained from our peeling approach. And so in summary, we obtained this sample complexity for learning elliptic operators, and we show that it is not just a theoretical device to answer this sort of, theoretical question of sample complexity, but it's really a practical method that can accelerate the learning of closure operators in computational fluid dynamics. And now, so that was the first part of the talk that that shows how thinking of numeric computation in terms of statistical inference, which led us to this idea of exploiting conditional independence in our in the underlying Gaussian processes, how that allows us to improve the operator learning of elliptic problems. And now we're going to go to a very differently flavored problems, which is hyperbolic problems. So in some sense, everything that we have been doing so far really is based on the regularizing effect of elliptic equations that leads to these like nice or smooth solution operators, and therefore the hierarchical lowering structure that we were exploiting. And now what I want to do is I want to show that this idea of using statistical inference ideas in numeric computation is not restricted to elliptic problems that are very naturally associated to Gaussian processes and so on, but there are at least equally as promising such approaches also in the case of hyperbolic conservation laws. So much more, much wilder equations, if you will. And so the equation that I'm going to talk about here is going to be the compressible Euler equation, barotropic compressible Euler equation. And so this is a sort of conservation, this is an equation of conservation for momentum and mass, and it's a sort of describes the motion of an inviscid gas. And so inviscid is very important because that means that we don't have any sort of elliptic operator that provides us with smoothness in our solutions. And in some sense, these equations have two sort of main modes of behavior. They can either behave like a kind of wave equation, like in sound waves on the left, when you have when basically the velocity with which particles are traveling is smaller than the speed of sound. And then for large velocities, you have the sort of transport behavior where the profile, the velocity profile is sort of vectored along itself. And as you already see in this, like in this transport behavior, in this presence of high velocities, you have this sort of slope steepening effect, where basically the gas here is moving faster because of the stronger positive velocity. And so it's moving faster to the right than the gas here. And as a result, the slope of the velocity keeps increasing. And if you keep going like this, then you form a so-called shock wave, which is a discontinuity singularity in the velocity and pressure variables, which really you should think of arising from sort of faster particles catching up to slower particles. And so it's almost inevitable in any kind of compressible gas that eventually you will develop these kind of shock waves, because there will always be some gas particles that are faster than the ones that are downstream from them, and so they're going to basically crash into each other, and that will create these shock waves. And so, in the context of shock waves, the way solutions are defined by analysts is as follows: that one says, okay, one regularize the equation by a little bit of viscosity, and then let the viscosity go to 0. And so basically, when one solves now, or hypothetically solves this the Euler equation with each finite value of viscosity. So here on the left, we see what happens with the law of viscosity. So things smee out very quickly. And then we add a little bit less viscosity, so things smee out a little less. And then we add even less viscosity, and things are staying relatively sharp. And so in some ways, the solution concept one is interested in simulating these equations is really this so-called vanishing viscosity solution, which is the limit of the solution of these regularized viscous problems as we decrease the viscosity coefficients. And simulating these kind of equations is important in many domains, in astrophysics, supernova, basically anything that explodes in space, all sorts of aerospace applications, anything that flies at fast speeds, and finally in medicine, where we are using, for instance, sound waves in order to destroy kidney stones. And so what this work is about is finding a way of regularizing these equations in such a way that they preserve a finitely smooth profile that allows that neither smears out nor develops these singularities. Because the problem is, if you for any finite amount of viscosity over time, you'll see a sort of smoothing out of the nominal solution that results in sort of a systematic dissipation bias of your solution. And so what this work is about is trying to find an alternative way of regularizing equation, not using viscosity, but something else that is going to keep these like smooth out shock profiles sharp and of the same shape throughout the simulation, and therefore avoid the excessive amount of dissipation induced by viscous regularizations. And so to derive this regularization, we can start with the case of the vanishing pressure in the 1D equation, where we can compute the solution of the problem using the method of characteristics. So if we say the pressure vanishes, that basically means we have a bunch of particles that are also moving independently from each other. And then we can compute the solution by simply at a given point sort of like seeing what particle is moving through that point at that time right now, and then tracing it back to the initial condition. And similarly, we can trace if sort of particles are more like moving into each other, away from each other, in order to find a closed form solution for the pressure, for the density. And so these sort of characteristics that one is tracing back when writing down solutions of these equations, they are really they should really be thought of as the path of individual particles. And from this perspective, and again, this is not so this is not yet a new stuff. This is sort of classical material and hyperbolic conservation laws, is that shocks form exactly when these particle paths cross. So here I've overlaid the velocity profile, so the u function u, and these characteristics traveling through space-time. And you see that the velocity develops a singularity, so infinite slope, exactly the moment that two of these characteristics are crossing. So because the moment two particles with a different initial velocity collide, you have to the left, you have one velocity, to the right, you have another velocity. And that's how, and that's why the singularity development in these equations very fundamentally linked to the sort of collision of characteristic paths. And so the key question is now how to sort of continue these paths after crossing. And then it is well known that in sort of vanishing viscosity solutions, the right way of continuing these particle paths is by letting them merge. So here you have two of these particle paths, and they collide, and then they continue with their average velocity. So what that really means that if you think of them as sort of right, if you think of them as like balls, it means that they are sticky balls. So they go in a straight line, they hit each other, and then they collide and merge and move with their average velocity. And these are kind of the solutions that one is interested in simulating simulating the Euler equation. But there's, I mean, the difficulty sometimes arises from the sort of like the fusing of these particles together. So it's a very singular operation. That's what makes this sort of challenging numerically. And we can even take a more geometric perspective on understanding this shock formation by now saying, instead of plotting the path of the two particles in the sort of like xt plane, so where there's kind of like a where basically x is the position and t is the time, and then we're tracing these two paths, we can also trace the joint movement of the two particles in this sort of like phase space, like where one coordinate corresponds to the position of the one particle, and the other coordinate corresponds to the position of the other particle. And so what we get this sort of time-dependent path that moves in this sort of joint configuration space. In particular, we see from this perspective that what happens with this path is that, and it's even easier if we rotate the coordinate system, that basically it moves along a straight line until it hits the boundary of the set where basically the set that is only accessible by crossing characteristics, and then it slides along the boundary of that set. And so in some sense, all shock formation arises from the problem that in the configuration space, our system reaches the boundary of this accessible set, the boundary of the set that prevents characteristics from crossing, and then sort of instead slides along the boundary. And some of the behavior at the boundary, that's where that is very singular, and that's sort of what causes these numerical difficulties. And so instead, what we are proposing is we want to regularize the geometry using what is called a barrier function. And so before I explain how this barrier function is going to help us create these paths, I want to show you briefly what I mean. So what we want to do is we want to replace these particle paths that you see in blue, which are the normal particle paths that sort of collide and then merge. We want to replace them with these particle paths that you, for different regularization strengths, you see in yellow, orange, and red, which are basically paths where the particles only asymptotically approximate each other or approach each other. Or like here in this geometric perspective, we are approaching this infeasible set only asymptotically without ever reaching. And the reason this is an attractive sort of mechanism is because this way we can ensure that we never actually reach the boundary of the set. So we never reach the point where things are crossing and things become singular. But at the same time, on the coarse scale, we obtain virtually the same behavior as in the nominal equation. So that's exactly what we want. We want a regularization that preserves the main features of the solution while avoiding the formation of singularities. And so in order to realize this regularization, we're going to use some elements of differential geometry. So in differential geometry, maybe one of the key ideas or so in differential geometry is the distinction between points and directions. So right, if you work in linear algebra, you think of vectors to both represent the position of something and also the relative displacement or the direction of movement of something. Where in differential geometry, we formally distinguish between them. So we think of positions of things on a manifold of being a priori something very different from sort of directions in which the thing could be moving on the manifold. And then the key object that sort of connects these two things, so connects the notion of a position and the notion of a direction, is the exponential map that says it takes a initial position p, which is sort of where you start, and then gives you the position that you would get by walking in the direction of v for a unit time interval. So this combines the direction v and the position p in order to get a new position. And so, for instance, in the case of linear algebra, this exponential map would be obtained simply by adding the position at the velocity, right? If you're in point A and you want to go for a unit time interval in point P and you want to go for a unit time interval in the point V, then after a unit time you end up in P plus V. And it turns out that these barrier functions, like the one I've shown you before, they allow to construct alternative such notions of exponential maps, so alternative ways of going straight in the direction. And so the way this works as follows: that we take our original point and velocity, we transform both of them using the gradient of psi. This is something called the mirror map in optimization. And then we walk on a straight line in this sort of mirror geometry. So we compute the sort of ordinary flat linear algebra exponential map in this alternate coordinate system. And then we map back. And so it turns out that by choosing our barrier function, sorry, I should have, wait, let me just go to back the barrier function. By choosing the barrier function such that it blows up as we approach this sort of infeasible set, we can ensure that the resulting alternative straight paths actually bend away from the constraint set. And so this gives us a way now to regularize the equations by saying we replace the ordinary notion of going straight that our particles abide by this modified notion of going straight that is defined in terms of these barrier functions that makes particles sort of steer away from each other as they approach each other. And so now we can do a bit of computation. So right, our straight lines have this form according to, because that's just how the exponential map, this like modified exponential map looks like. And then we can take two derivatives to get basically an alternate equation of inertial movement. So right, if psi were just the quadratic, like in the ordinary Euclidean case, then this term would drop out and we would just get our ordinary equation of inertial movement, which is just phi dot equal to 0. And now instead we get phi dot equal to this curvature term on the right. That modifies the motion to avoid the boundary of this set. And this idea generalizes. This idea now allows us to sort of modify our original Euler equation, or in this case Burger's equation, because we are still working with the zero pressure, by saying, okay, we replace this like ordinary notions of straight lines according to which particles fly with these dual straight lines. And now what we want to do next, we want to extend this from just like two characteristics to an infinity of characteristics. And so the way we can do this is that instead of viewing these characteristics phi of x1 or phi of x2, which are the characteristics starting in point x1 or point x2, we can view the evolution of the entirety of characteristics as a path in function space. So in basically an L2 geodesic. And it turns out that, so this is like an old perspective due to Vladimir Arnold, that the solution of the Euler equation, they're all sort of, they're basically all dynamical systems on manifolds of diffeomorphisms, so manifolds of deformation maps. And so, for instance, the incompressible Euler equation is the geodesic equation on the manifold of volume-preserving diffeomorphism maps. In a similar sense, the compressible Euler equations are dynamical systems on the manifold of general diffeomorphisms. And the nice thing is that from our perspective, actually not much has changed. So as before, right, now the point where these characteristics cross, this is also the moment that our deformation map leaves the manifold of diffeomorphisms, because the moment these characteristics cross, we have a derivative equal to 0. So the inverse is, so the inverse is not differentiable anymore. So this phi is not a diffeomorphism anymore. In some sense, also for our sort of picture of staying inside of this sort of feasible set, we get exactly the same picture, just that on the y-axis we don't have this relative difference in position of the two particles, but instead we now have the derivative of our deformation. And so we can basically take the same construction that we used before, just that now we replace the sort of pointwise we replace a sort of pointwise constraint with like an integral over this constraint. So an integral over the Euclidean norm here on the left. So that's just the Euclidean, the ordinary Euclidean part. And then our regularization term becomes the integral over the log derivative of our diffeomorphism. So, and as before, as we are approaching the boundary of the manifold of diffeomorphisms, this derivative gets close to 0, so the negative logarithm blows up. And that's why, again, we can expect these modified the modified notions of straight lines to sort of steer away from the boundary of the constraint set. And so I want to show you some examples for this. So first of all, we get the nice sort of, so here you see basically blue the nominal solution, the ground truth, and in red you see the solution of an equation of this regularized equation, and you see that you basically get the same long-term behavior, with the only exception that the regularized equation has a slightly smoothed out shock profile. And so for instance, one sort of frequent way of framing this problem in numerical analysis of conservation laws is that basically you could either choose a viscous regularization like this Lax-Friedrich method, where your shocks or your solution is going to smear out excessively over time. So that's like this just viscous regularization. Or if you use a higher order scheme like the Lax-Vandroff method that does not have this viscous regularization, then you tend to develop these Gibbs phenomena. So that's what you see in yellow, these Gibbs oscillations close to the shock. And what it turns out that what is quite effective is to combine these sort of standard higher order methods with this modified equation that is obtained by smoothing out the shocks according to this geometric principle, because that tends to both avoid the excessive viscosity of the Lax-Friedrich type, so the viscous regularization, while also avoiding the Gibbs oscillations due to the Lax-Vandroff. And this is also very nice because, for instance, in a problem like this where you have both, so this is like a shock wave on top of a sound wave. There it can get quite tricky to distinguish between what part of this is a shock wave that you have to deal with and that needs some energy dissipation, and what part of it is a sound wave that you want to keep as is. And so this is also something where this regularized method combined with Lax-Vandroff performs quite well, almost matches the reference solution, whereas the Lax-Vandroff method, due to the Gibbs oscillations, overemphasize the sound wave, and the Lax-Friedrich just straight out dissipates the sound wave away. So we also have some numeric examples on 2D problems. So for instance, here you see some sort of like shoulder on shoulder collision of two shock waves. So here this shock wave is moving to the right, this one's moving to the left. And so again, you see that this Lax-Vandroff with our information geometric regularization is able to preserve many of these sort of fine features that get lost if you use a purely viscous regularization. And that's also reflected in the way it keeps track of the total energy. And even after very long time horizons, we see that this Lax-Vandroff with information geometric regularization preserves the Lax-Vandroff with information regularization preserves sort of sharp gradients in the solution. And now I want to before like the last point I want to make before finishing is that is the following, that so far I've shown you the sort of geometric regularization part. So why do I call this geometric regularization? But I haven't explained to you why this is called information geometric regularization. And that points to sort of the bigger vision of this project, which is why I want to briefly comment on it. And so there is this so if you take the probability simplex and you can equivalently define a barrier function for the probability simplex, which is given by the negative Shannon entropy, and this sort of basically the analog of this sort of modified notion of straight line in this example here, where the barrier function psi is the Shannon entropy, and the set over which we're working is the probability simplex. This is a very, in some ways, it's the canonical notion of a straight line on the probability simplex, so on the family of probability distributions, and because it is invariant under information preserving mappings, it is geodesically complete, meaning you can it never leaves the probability simplex, and it is flat. And so now we can look at our regularization term and observe that this regularization term really is nothing but the Shannon entropy of the mass density of our Euler equation. And so from that perspective, it really amounts to we can think of basically the ordinary Euler equation as being associated to using the Wasserstein geometry on the mass density. And then this sort of regularized equation that I've just described is in some sense uses a regularization of the Wasserstein distance with the KL divergence. And so in that sense, it's a bit similar in spirit to entropy regularized optimal transport, but now in the case of problems where we're solving for dynamics as opposed to a solving a problem for two fixed endpoints. And this is in some sense, this is sort of the starting point for a much bigger research project that I like to call information geometric mechanics, is that we can really go one step back and see what are the underlying physical models below the Euler equation, and that takes us to what is called the Boltzmann equation, which describes the motion of a gas as a sort of motion of a probability distribution in phase space, so position times velocity. And it turns out that the Euler equation for the ideal gas case can be obtained by using a particular ansatz, the so-called Maxwellian ansatz for this Boltzmann equation. And it turns out that the regularization that I've shown you is really exactly the entropy of this distribution. So in some sense, what this amounts to saying is that we treat the solutions of our continuum mechanical laws, so in this case the Euler equation, we don't treat them as a sort of governing representative volumes that are subject to the geometry of particles. So we think of like a piece of solution being like a tiny piece of matter that moves according to towards the right geometry for particles, but rather we think of our continuum mechanical equations really as governing probabilistic description of microscopic realities. So in this case, probabilistic descriptions of, or probabilistic summaries of the solution of a Boltzmann equation. And accordingly, their solutions are then basically the parameters of these probabilistic models. And so as a way of sort of evolving them in time, we should not be using just the particle geometry, but we also should be using this sort of the natural invariant geometry on probability distributions. And that is sort of this I guess it's this bigger vision that this leads to, that I want to leave you with, is this idea of saying, okay, all our macroscopic continuum mechanical models are really just governing parameters of probabilistic summaries of microscopic behavior. And so as a way to analyze them, to numerically solve them, and so on, the natural notion of geometry is maybe not that of individual particles, but rather that governing the evolution of probability distributions. And with that, I'll be happy to take any questions. Thank you for your attention.
Yeah, thank you very much. Thank you. Any questions or comments?
If you can go beyond hydrodynamics, can you deal with solitons?
Honestly, I know very little about solitons. So what is a good? I mean, in principle, I think that maybe one way of thinking about it is that where I think this kind of methodology is most interesting or useful is in cases where one has sort of energy dissipation or some other regularizing effects due to sort of microscopic entropy-driven behavior. So for instance, I guess viscosity diffusion, for instance, in the case of fluid dynamics. And so I don't know if that plays a role in solitons, but I'd be very curious to learn more about this.
Okay. How about singularities like Ginzburg-Landau. Your method sounds like if you deal with PDEs, and that's your basic premise or tool, then maybe you can deal with tough situations like Ginzburg-Landau.
Yeah, so basically in some sense maybe like on a technical level, the main feature that to identify where this method is most useful is probably are cases where there's some kind of inequality constraints that are include. So where, for instance, right, in the case of the like fluid dynamics, you don't want like mass to penetrate through mass, so you have like a positivity constraint of that kind. And I think, I mean, in some sense so I don't know for Ginzburg-Landau if there are like I mean, to be honest, I don't know much about this equation either, but basically if you have, for instance, any kind of inequality constraints, even if they're sort of like hidden, and then oftentimes what sort of like some like viscous regularization or so is really doing is it sort of is ensuring these sort of inequality constraints, kind of like similar to like a barrier or penalty method that keeps you away from violating these constraints. And so in some sense, this information geometric regularization is helpful because it allows you to enforce these kind of constraints with less perturbation to the overall long-term behavior of the solution.
Okay, very promising approach and methodologies. I learned a lot. Thank you.
Thank you.
Welcome.
Thank you. Other questions or comments? Okay, seems not. Yeah, thank you very much, Florian, for the nice talk. And thank you, everyone. And so we'll see you all next week. And Florian, hopefully in a month in Toronto. Yeah.
Sounds good. Thank you all.
Yeah. Bye.
Bye-bye.